Yeah, I haven't given a presentation since college, so bear with me if it's a little bit not great. So, yeah, I've just been sort of screwing around in my free time. And in this case, I don't know how much of you guys are familiar with these. Project Euler is a website that has a lot of various problems that are available to solve, and they're of various difficulty. This is one of the most recent ones. It's called friend numbers. And you're not supposed to discuss them, but I'm not going to give away the answer. Actually, I didn't manage to get the answer, so I can't do that. So I think it's all right to just sort of discuss the process and how to approach the problem. So, yeah, it's a pretty simple problem as far as structure is concerned. Let's call two numbers friend numbers if their representation in base 10 has at least one common digit. 1,123 and 3,981 are friend numbers. Let f of n be the number of pairs pq with one less than or equal to p less than q less than n, such that p and q are friend numbers. F of 100 is equal to 1,539. Find f of 10 to the 18th mod 1 billion something. So basically, friend numbers is a pretty simple concept. There's no friend numbers less than 10. A friend number for 9 would be 99 or 19 or 109 or 901 or 929, any other number with 9 in it. So, on to the next part. So just to sort of make sure that I knew what the question was asking, I wrote an initial program in Go, which is just sort of the brute force method. So this is a pretty simple program. What it does is there's four for loops. The first one loops through all the numbers less than the target number, so less than x in this case. So if we're finding f of 100, it's all the numbers less than 100. The second loop loops through all numbers that are less than the number that's currently being looped through in the first loop. These two loops turn those numbers into arrays that contain the digits in each number, and then the following two loops loop through the arrays and compare each digit to each digit in the first number to each digit in the second number. If they find a match, they immediately add 1 to the count and then break out of all the loops. Well, they break out of these two loops and go to the next number in the second loop. So here's a little bit more clear way to think about it. So if you say f of 1,000, x will eventually get to 123. The third number that y will loop to will be 3. Yeah, will be 3. Right? Yeah, so this should be a 3. So x will be 1, and then it'll loop through all the digits in y. It'll find 3. It'll compare the two, and it'll say, OK, that's a pair. Add to the counter, increment y to 4, and then, yeah, well, first break out of the comparison loop so you don't record two friend numbers for a single pair of numbers, which is a big problem eventually. So problems with the Go program. The main problem is that it's way too slow. We're dealing with 10 to the 18th, so if you wanted to brute force this method, even if every single calculation only took a single instruction, it would take years to solve, potentially decades, probably much longer than that, using a standard laptop. So this isn't going to work. But at least we know that this number, 100 is equal to 1539, matches the original description in the original problem description. So we know at least that we have the concept down, right? We're on the right track. So a more efficient method, counting in iterations. So assuming that you have a set of numbers that are all equivalent to each other, in order to find the number of friend numbers in that set, you have to basically compare each number in the set to each other number in the set. Because since they all contain the same number, they're all going to be friend pairs. So you basically just have to find the number of pairs. So for instance, a set with 4 numbers in it, we just need to find every single combination of these numbers. This comes out to 6 in a 4-element set. So we can calculate that without counting them explicitly with this function, which is called g. I just call it g. So for s being the size of the set, g of s is equal to the size of the set minus 1 squared divided by 2 plus the size of the set negative 1, minus 1 divided by 2. So in this case, the size of the set is 4. 4 minus 1 is 3. 3 squared is 9. Divided by 2 is 4.5. Plus 3.5 is equal to 6. This works with much larger numbers than 4, luckily. In fact, it works with any size number. So that's very useful. If every single number in less than 10 to the 8th had the same number, was the same number, we would essentially be done. We could just find g of 10 to the 18th and input that as the answer. Unfortunately, that's not the case. So, how to calculate f of 10 to the 18th? Right, so let's just imagine that instead of saying that 10 to the 18th, it all has the same number, we'll break it down into numbers that have 0, numbers that contain 1, numbers that contain 2, and so on. So we take g of a being the set of all integers less than 10 to the 18th that contain 0, g of b being the set of all integers less than 18 that contain 1, and so on up to 9, add up all the g's, the product of all the g's, and we'd have the number if we only had the numbers 0 to 9 less than 10 to the 18th. Unfortunately, that's also not the case. So some numbers will be counted twice. Because we have numbers that have multiple digits, such as 123 or 2,178, or much larger numbers that might contain every single digit, we have to subtract the numbers we count because we'll count them too often. So we'll count 123 3 times because it has 3 individual digits, 1, 2, and 3. We'll then subtract it for each set of pairs it has. So we'll subtract it for 1, 2, 2, 3, and 3, 1. Now we've counted it 0 times, so we have to add it back in. Strangely enough, the way that this works is that it alternates every other set. So you add the first, you subtract sets of 2 digits, you add sets of 3 digits, you subtract sets of 4 digits, and so on. It's kind of strange how this works. I'd have to think about it a little bit more to figure out exactly why it works that way. But is this right? Yeah. Okay. Yeah. So this is the same principle, just with larger sets, right? 1-digit set, 2-digit set, 3-digit set, up to 9-digit set. Here's an example for a 10-digit set, right? It has 1 10-digit combination, no, it has 10 1-digit combinations, which you add, and then subtract 45 for the 2-digit combinations, add 120, subtract 210, add 252, so on, so forth, until the last one is the 1 10-digit combination, which is just all the numbers, which you subtract, and then you've counted it exactly 1 time. So this is very useful. We just have to find g of all the sets of 1 number, and then add that, and then subtract all the sets of 2 numbers, and then add all the sets of 3 numbers, and subtract all the sets of 4 numbers, and so on. But what do we take g of? Because unfortunately not every number less than 10 to the 18th contains a 1 or a 2 or 3 or 4 or 5 or so on. So we have to count the combinations of numbers that are less than 10 to the 18th that contain each number. Also, because, for instance, all the numbers less than 10 to the 18th contain 1 a certain number of times, that is equal to the number of numbers less than 10 to the 18th that contain 2, which is equal to the number of numbers less than 10 to the 18th which contain 3. But 0 is a special case because, for instance, if we have the number 1,000,000, then for all the numbers from 100,000 to 200,000, those numbers all have a 1. But for numbers less than 100,000, those numbers do not necessarily have zeros. So we're going to have less instances of zeros than all other digits because zeros cannot start numbers. So in order to figure out how many times a number appears less than 10 to the 18th, we have to set up basically what is a recursive function in which we calculate the number of times that a number appears in the first 10 digits, and then use that to calculate how many times it appears in the first 100 numbers, and then how many times it occurs in the first 1,000 numbers, and then so on and so forth. So this actually isn't that difficult. We only have a few individual cases, and we'll discuss them. One of them is, well, for the most part, we have to figure out possible combinations. So, for instance, in this case, numbers that contain either 1 to 9, one of the digits from 1 to 9, or 3 of the digits from 1 to 9, less than 1,000. There's 3 possible digits. There's 6 possible combinations of those digits. If you add in 0, it can't be the lead digit, so there's only 4 possible combinations. We have to get these numbers first so that we can use them in the recursive function in order to add up to the number of numbers that contain given digits less than 10,000, less than 100,000, and so on. But you can see that, for example, here, right, we have 2 numbers between 1 and 9 and a 0. This leads to, sorry, these variables represent combinations of variables from here. So this E references this E here, and this E references this E here. So this E goes into this E, this F, and this D all go into this, which forms this E. Then that goes into this, which along with the F and D from here form this E, right? So there's a lot of numbers that are fitting into numbers, which are fitting into numbers, which are fitting into numbers, which are fitting into numbers. It's not possible to do it with pen and paper, clearly. It would take a million years. So that's what the whole point of the recursive function. So this is just an example of that, right? How to come up with a definition for how many times, or to count the number of times that a number appears less than, for instance, 10,000. So 1 and 2, right? So 1 and 2 are going to be in every number between 1,000 and 2,000, or 2,000 and 3,000, for instance, between 1,000 and 2,000, you will always have a 1 in front. 1,019, 1,099, 1,317, 1,554. They all have a 1 there. So you just have to figure out the number of times that 2 occurs. Similarly, with the numbers between 2,000 and 3,000, you just have to figure out how many times a 1 occurs. But for all other intervals, between 0 and 1,000, or between 3,000 and 9,999, you can't do that because you don't have a 1 or a 2 in front. So in that case, you'd count the number of times that 1 or 2 exists in the set of numbers, the interval between 0 and 999. So if you go back here, right, this is the combination. Well, the actual combination is, right, this one, which is b times 2. Here, b represents the intervals 1,000 to 2,000 and 2,000 to 3,000, and d represents all the other intervals. And that's how you find that number, right, by combining those sets. Okay. So here's the recursive function. I wrote the first one in Go. I wrote this in Python because Python has native handling for arbitrarily large integers, and that's really useful when you're writing something like this, because to do it in Go would just be a complete nightmare. Also, it's easy to learn, which is good because I don't really know Python, so I just sort of like scrap this together. So here's your recursive function, right? Here's your base combinations function, which finds that 4 and the 6 are from original. So if you have 1, 2, and 3, they can go together in 6 different ways. That's what this basic combinations function does. It has 2 different cases, one if 0 exists and one if it doesn't. Our second function is find combinations. So this is the actual recursive function. It has 4 different cases. One is a case in which you have a certain number of numbers from 1 to 0, or from 1 to 9 and a 0. One is a case in which you don't have a 0. These cases cannot be made out of these. These are either you have 1 0 or you have only one integer that is not 0. And these need special definitions. Specifically this one, because it actually takes, for instance, if you're dealing with numbers less than 10,000, it uses 1,000 as one of its, right, math.pow 10 upper limit minus 1. So it's going to integrate 1,000 into that choice because, for instance, if you have the numbers less than 10,000, every number within the set from 2,000 to 3,000 will have a 1 in it, right? Or from 2,000 to 3,000 will have a 2 in it. So, yeah, this works, surprisingly. And this is pretty much the end because so then, right, we take that and we integrate it into our G function, We integrate our g function into it. And then we take the combinations. These are the combinations of possible ways that numbers can be combined. So you have to take, basically you have to run the recursive function and multiply it by the number of combinations. For instance, this is the number of combinations that can exist between 3 non-zero integers and 0. So that would be, if you have 1, 2, 3, 0, it's every way that you can mix those together. So yeah, that's that. And then take combination just runs the recursive function over it, and then takes g of that number, which is very large because it involves squaring it. Well, first of all, it's a big number in the first place, and then you have to square it. So this is, yeah, the 1 you add, the 2 you subtract, the 3 you add, and that's all expressed here. So you end up with this really large number, 4.99 times e to the 35th, and then you take it mod a billion, and for some reason it doesn't work out. And you might be saying, well, why did you explain that if you got the whole problem wrong? Which is a good point. But the program does successfully solve it for the case of 1,000, because we can compare that with a brute force program. And this is the same number that the brute force program comes up with. So we know that it essentially works. I just don't have, right, 289,665. Just not quite sure why it's not functioning for the much larger set. So yeah, that's about it. Yeah, it took me a while to think about that, but does anybody have any questions?
Does it have any real-world application?
I'd be hard-pressed to come up with one. Yeah, I mean, I would assume that, like, typically, even purely mathematical problems end up having applications in the sense that their solution is applicable to something somewhere. Maybe cryptography, you know. I'll just throw that as that's the one you can always say. Yeah, it's useful for cryptography or something. Yeah, I'm not quite sure exactly what it could be used for, but it's definitely interesting to think about. Yeah, Sasha?
Is there like a solution on the website, or can you see like?
Yeah, that's why they ask you to give it mod a billion 267. They don't give you the solution, so you can't see it, and I'm not going to look it up because I could still probably think about it for a little bit longer and maybe figure out where I went wrong.
But is there like you could check there's like a reference implementation or like?
You can check if you're wrong, and then if you get it right, you can see how other people worked through it, which is very useful unless you don't know the solution in the first place, in which case it's not very useful. Yeah?
How long to compute the result?
Oh, yeah, okay. So it's actually not, I mean, it's, you know, longer than a few microseconds, but it's like 15 seconds or something. Maybe not even that, maybe 5. Yeah, it's quite fast, which is quite useful.
So did they give you hints in which direction to go, or do you have to figure out?
The hint is essentially the first example that they provide you with this number. So you at least know that you have the definition correct, right? Because if you can compute this number using the brute force method and it matches with the value they give you, then you know that you know how they're defining f. And your definition of f is the same as theirs.
I guess once you have the brute force method, like going to the smart method is kind of a big jump. Like you might get stuck at the brute force.
Yeah, for sure. But I mean, you'll never solve the problem using the brute force method because it's just not. I mean, that's why they make it 10 to the 18th, so that you can't. Some of the early problems, they'll give you a number that you could easily brute force, and then they'll tell you, oh, 200 problems from now, we're going to give you the same problem. It's going to be 500 million times bigger, and you're going to have to redesign your algorithm because it's just not going to work. Right, yeah.
Something you could do is like maybe compute the modulo every time at every step, so you will get the same number at the end, and your number will get less big. So maybe that's why you.
Oh, I see. Yeah. I mean, that's definitely possible, and maybe it could be the source. I'm not sure how. I assume that Python is accurately handling, right? but maybe not. And definitely if not, then it could be. Actually, you know what? Maybe somebody might have insight on this, because I redesigned the algorithm at one point. It was wrong, and I redesigned it, and because I caught the mistake. And it still gave me the same number, modular, whatever. So that seems suspicious to me, that I was like doing the multiplication or addition in the wrong number, and I was still getting the same modular number as I was once I reorganized it in the correct order. So maybe it is that Python is just handling the modulation wrong, and I just need to rewrite it so it does mod with every step. That's a good idea.
Using 2 or 3?
Huh?
Python 2 or 3?
This is 3, I think.
That makes a big difference.
Oh, does it?
Yeah.
Oh, okay. See, this is why I gave this. This is why I came here, right? This is stuff I don't know. Right.
Yeah. Also, whether you use float or decimal makes a big difference in Python.
Right. What is? I mean, if I'm just writing down something.
Decimal is a module that you import to handle decimal numbers from.
Right. So these are all integers. It shouldn't be doing anything with decimals whatsoever.
No, there's no division.
No, the only instance in which it divides something is if it might divide a number in 2. I assume it can handle halves without getting that wrong. But maybe not. In which case, I have another thing to check. Okay, yeah, I'll definitely do that. Great, thank you very much.